Okay, that says we are live.
All right.
Hey everyone, welcome to Universe at Home. I'm Lauren Laufman, and I am a second year grad student in astrophysics.
My name is Trevor Knuth, and I am a fifth year astrophysics graduate student.
So today's talk is going to be about asteroids and meteors. Fun fact to start with, this photo that I took right here in the background is of Meteor Crater, Arizona, which you will find out more in later in the talk. To outline today's talk, first we're going to go over some vocab and background info, like what's the difference between an asteroid and a comet and a meteor. Then we'll talk about some historic impact events and a notable near miss last year, and then some info about meteor showers, some cool stuff about spacecraft that have visited asteroids and comets. And then Trevor and I will take questions, which you can type in the little chat box that should be to the right of the YouTube video. After that, I'm going to open up a program called Universe Sandbox, which you can use to show really cool simulations of like solar system stuff. And yeah. So, what are asteroids and comets and meteors? First off, asteroids are exactly what you think they are. Big chunk of rock and metal, typically iron and nickel, out there in space orbiting the sun. Comets are a bit more involved. They have a nucleus or core made up of ice and dust and some rocky material. The coma is the envelope around the nucleus of the comet, which forms when the comet passes close to the sun, because the heat of the sun turns the ice and dust kind of into gas. And then as the comet gets closer to the sun, this ice and dust and gas gets pushed further out by the solar wind. And that's how you end up with a tail on the comet. And this is why the tail of a comet always faces away from the sun, whether or not the comet is moving towards or away from the sun itself. Meteors are when these asteroids or comets actually enter the Earth's atmosphere and are burning up. Some examples of famous comets are Halley's Comet, right here on the left. It's super bright, comes every 76 years, last seen in the 80s. The Neowise Comet, that has been dominating the news for the last several weeks because it was super bright. And Oumuamua, the first interstellar visitor, an object from a different solar system that came to visit our own solar system. All three of which I can show you some cool simulations of in Universe Sandbox later on. So, how close have we come to total annihilation in the recent past? Well, you will find out. Dangerously close. First up is Meteor Crater. This is a meteor crater about 40 miles east of Flagstaff, Arizona, with a very original name. It is also known as Barringer Crater, after Daniel Barringer, who was the first to suggest that the crater was from a meteor impact. He was right on that account, but he incorrectly thought that the iron-nickel core would be buried beneath the crater, so he tried digging for it. However, like most asteroids, they get pretty much vaporized on impact, leaving only a few remains. Some cool fun facts about this. This was 50,000 years ago, so relatively short on a cosmic timescale. And the crater is really big. It's almost a mile in diameter. And astronauts actually trained at the bottom of the crater for the moon landing. In the middle of the crater at the bottom, there's actually a cute little, like, not cardboard, but cutout of an astronaut so that you can see for scale. And in this picture on the right, there's me with, well, I'm not the person in the middle, but to the left of the middle, because I've been there. These next two pictures on the next slide are a couple more photos that I took of Meteor Crater. On the left is the largest chunk of meteor that's been found to date, along with some random kid who was in frame and my friend Tomas for scale. On the right is a picture that I took from an airplane, where you can see Meteor Crater in the bottom right, where it looks really small from that high up, and the mountains that surround Flagstaff in the background in the upper left. Next recent disastrous event was the 1908 Tunguska event. This was from a meteor bigger than the one that made Meteor Crater, 300 feet in diameter. However, this one actually exploded at an altitude of about 5 miles above the ground. So we don't actually have an impact crater from this, but the shockwave flattened 80 million trees over a square area of 830 square miles over an area of 830 square miles of forest. This was equivalent to 20 megatons of TNT. So that's kind of terrifying to think about. And luckily, there were very few deaths because it was in a super isolated area of Russia in 1908. But if it were to happen over modern New York City, it would be a complete and utter disaster, and it would flatten all of downtown, even if it were exploding at 5 miles above the ground. Another more recent event, also over somewhat middle of nowhere Russia, is the 2013 Chelyabinsk meteor. Forgive me if I can't pronounce it correctly. Trevor, can you start the video? So this is just a short little clip that it'll play of the meteor that exploded again in midair, but it was as bright as the sun, and the shockwave damaged 7,200 buildings, which is kind of crazy. No deaths, but 1,500 people were injured, mostly by the shockwave destroying all these buildings and everything. And it was felt up to 16 miles away. Just to drive that home, this thing exploded 20 miles above the ground, and it still damaged so many buildings. And it's coming in at 43,000 miles per hour. So this is like a house going through your atmosphere that weighs 1.3 Eiffel Towers and exploding and destroying a whole bunch of buildings. So that's also unpleasant to think about if it hadn't exploded so high up. This next slide is a little comparison between the two. So you have the Tunguska event on the right. That's the size. Then you have the Chelyabinsk meteor, which is a lot smaller, but it literally weighs more than the Eiffel Tower, which is pictured next to that. So that's wild. You might be wondering how come certain asteroids explode midair instead of creating an impact crater. This is because of the angle that the asteroid ends up coming into the atmosphere at. So like if it's really shallow, it might kind of skim off of it, but if it's coming like straight down, like it might be a lot more likely to cause an impact. Last year, the 2019 OK asteroid came within 1/5 of the distance to the moon, and it was not spotted until the day before. This is because it was coming basically straight, like if you were to look at this asteroid, it was coming from like right next to the sun. So our telescopes, which are looking at night, did not see it because it was only visible in the daytime from right there, and it was coming pretty much right at us. It is estimated to be bigger than the Chelyabinsk and Tunguska meteors. So this thing could have been an extreme disaster, and we had no preparation. Now, you might be really worried at this point, but asteroids this size actually pass by pretty often, and this was an exception to having not been spotted any time earlier. So, yeah, and right here on the right is just kind of a picture of the orbit. So, those are all giant, drastic, terrifying, huge impact events. But meteor showers, a lot more common, a lot less disastrous, a lot cooler, a lot more visible. So, what causes a meteor shower? You have a comet that's traveling through space and it leaves behind a trail of debris. As we discussed earlier, the sun is blowing off this ice and dust and bits of rocky material behind. Sometimes these trails are directly in Earth's orbit, and so every time at the same time of year, the Earth goes through the remains of what a comet leaves behind. Now, these tiny little particles that are left behind are actually on the order of like a grain of sand or the size of maybe a small pebble, and they barely weigh a few grams. Yet they're traveling like tens of thousands of miles per hour and going through the atmosphere about 50 miles above the ground and just creating the brilliant flashes that we see, which are really cool. On the next slide, here's a little bit of a better explanation of how these meteor showers form. And so it's kind of another way to think of it is like, imagine if Earth's orbit is your regular commute to work, and the debris from the comet is like ice on the sidewalk that no one will shovel. So you slip on it at the same time each day on your commute. But even you slipping on the ice every day doesn't remove it all. Likewise, Earth going through the debris trail only removes a small amount of the particles. So there's still enough left for next year when Earth goes back through and when you slip on the sidewalk again.
All right. Speaking of meteor showers, we are currently within a period of a annual meteor shower called the Perseids. If you want to view this meteor shower, if weather permits it, although it's kind of cloudy today, as it often is in Minnesota, what we want to do is tonight look north to northeast, a bit sort of down from the constellation of Cassiopeia. That is this W-shaped constellation. It's called the Perseid as it appears to be coming from a point very near the constellation of Perseus. And we are currently in the very middle of the peak. So peaks between August 11th to August 13th. Um, the comet which actually created the Perseid meteor shower is called 109P Swift-Tuttle. You'll see that many comets have these very sort of peculiar names, kind of slammed together a lot of different things, because in astronomy you have to name a lot of objects, so you have to use a system that can name a lot of different things. As the example of sort of how fast these particles are coming into the atmosphere, like creating the meteors, you'll see, if you can see this event, is about 58 kilometers per second. And at the peak of this event, you should be able to see about 100 meteors per hour. A little more clear picture of where you can see this. So here again is that constellation of Cassiopeia, a very famous sort of star cluster constellation called the Pleiades. It's sort of going to be right here. If you look between Pleiades and Cassiopeia, you can find the constellation of Perseus, and in that area is where you'll be finding all these meteors coming. All right, so as Laura mentioned earlier, we're going to talk a bit about also visiting comets and asteroids. So because these are very massive objects, the ability to actually go to them has always been a possibility that has really intrigued scientists. And so here was a spacecraft mission to the comet, Rosetta. So this was done by the European Space Agency. It launched in 2004. The spacecraft, its name was actually Rosetta, but launched in 2004 and arrived in orbit in 2014. So it took 10 years for the spacecraft to actually travel through space and reach this object. Upon reaching it, it orbited for 17 months, collecting data and things like the images created here at the top right. Also, during this orbit, it released a small probe called Philae, which when it landed upon the surface of the comet, because these are so much smaller, you have to actually use some sort of method to actually make the probe land and sort of attach to the object. And so Philae used a 2 harpoon system, whereupon, bouncing, it fired it, kind of reel itself back in. Unfortunately, after it did so, you can't really control too many of the details of that impact. It settled in a shadow of a cliff, which I'll show a picture of in the next slide. And because it was in this sort of shadowed area, it wasn't receiving any solar energy, and so its solar panels couldn't collect power. And unfortunately, it died after about 2 days of sort of collecting images and sending that data back to the orbiter spacecraft. And then show. All right, so here is a orbital sort of chart where the blue is the Earth, so this is kind of going off in a circle. Pink is the Rosetta spacecraft. You can see kind of got whipped around. We usually will take spacecraft and send them very close to other planets to create what's called a gravitational assist or gravitational slingshot. Basically use the gravitational force of planets to sort of speed up your spacecraft and kind of whip it to where you want to go. And so all of these are, really finely calculated equations to sort of figure out what we want to do. And you can see eventually it kind of comes out and it connects with the 67P, the name of the comet it was trying to get to. As sort of it approached the object, because these are, again, not super massive things like planets, you have to use things like propulsion to actually sort of control the orbit of the object around. So you kind of got these really weird things where it sort of released those jets, got really close and did its orbit and kind of try to get to all these different angles, see the object in sort of every way that it can. As I mentioned before, Philae was the little probe that got sent to it. And so here you can see the actual picture of the cliffside that unfortunately got stuck behind and got enshadowed. The little sort of snow and kind of granulations that you're seeing in this image is not due to anything actually kind of coming off of this object. It's due to what are called cosmic rays, which are these really hyper energetic particles which can come from the sun as well as extra solar sources like supernovae. They're really high energies, and they come in and they hit our detectors, and they create sort of a false response. But yeah, this is an image of an object, a little tiny probe landing on something 252 million miles from Earth. It's extremely impressive for the scientists and engineers to make this whole thing work as well as it did. Another mission was to the object, the near-Earth asteroid called 162173 Ryugu. This was the Hayabusa 2 spacecraft. So this spacecraft launched in 2014 and arrived in orbit 2018. So a lot of times, sort of the orientation and position of different objects can create huge differences in the amount of time it takes to get there. This was a sample return mission, so a little bit different than Rosetta. It didn't just go send a probe and take images. It was actually intended to collect bits of it and actually come back. And so while it got to the object in 2018, it took its samples and it left in 2019, and we're expecting it to return to Earth sometime this year. The way that it took those samples was that it blew a hole in the asteroid in order to get these deeper samples, so not just the surface material, but get a little bit something that was beneath it. Sort of blow it open, collect that material, and then sort of get back. It did this by also sending an adorable little rover called Mascot to investigate the surface. I believe, yeah. All right, and so then here is the actual impact, creating an artificial crater for that deep sample collection. So you can see different images of that impact occurring. Then here you can see the Hayabusa 2 catching up with Ryugu, as opposed to the previous mission, that Rosetta mission, which tried to sort of maintain an orbit. This one didn't really want to orbit and get too sort of attached to the asteroid because it wants to come back. So instead, it's kind of got really close to it, cruised along with it, and now it is sort of trying to get back to Earth. All right. Another mission is the OSIRIS-REx mission. So this was a other sample return mission, but this one is being sent to the asteroid 101955 Bennu. This one launched back in 2016. It has arrived in orbit in 2018. By the time it's expected to come back will be 2023. So again, you're seeing sort of, a 10-year gap between launch and arriving, a 4-year gap, now a 2-year gap. And so all these things things get better over time with different rocket launches, as well as opportunities of sort of where are planets and other objects. This asteroid is interesting because it's considered a time capsule asteroid, which means it has very little geological change. If you consider the surface of, say, the Earth, where you have things like volcanoes, impacts, erosion, and plate tectonics, the surface gets changed a lot over the course of 4.5 billion years. Whereas this asteroid has seen very, very little change. So the structure and composition of it is basically the exact same as it was when it first formed billions of years ago. It's noted for having carbonaceous material. This is a necessary element for creating organic materials of life. And so it's very interesting to see sort of a method of actually seeing what was the composition and distribution of these elements way back in the formation of the solar system. This spacecraft, upon making surface contact by the TAG-SAM robotic arm, it will release a burst of nitrogen gas, which will sort of blow this regolith particles smaller than 2 centimeters into the sampler head, kind of basically suck up some of this regolith, and then it will blast off. There are different sites on the asteroid that they were sort of considering to be going to. They gave them these different code names of Nightingale, Kingfisher, Osprey, and Sandpiper. Eventually, they chose the site of Nightingale as the primary sample site, and then Osprey is the backup site. All right, so here is the image of the asteroid, and so it's kind of a peculiar looking one. Then here you can see the Earth orbit in blue. Pink is the OSIRIS-REx mission, and so this one's a simpler one because, again, this is a near-Earth asteroid, so it's not as far away as many of these other ones were, and so this mission is to go, collect these samples, and then come back. All right, another one, this is a planned one, is called Psyche. So Psyche is going to be an orbiter mission to the metal asteroid of 16 Psyche. So a metal asteroid is noteworthy because there are basically 3 types of asteroids. You have the stony ones, which are kind of made of almost Earth-like rock. You have metal ones or iron ones, which are made almost entirely of iron and nickel. And you have a fusion of the two called stony iron. So this is a considered very metal-rich asteroid. It's planned to launch in 2022 and it's planned to arrive in 2026. 16 Psyche is the heaviest known M-type asteroid, so metal type, thought to be exposed iron core of a protoplanet. So a lot of time these sort of things will be created in the early solar system with these little protoplanets, these sort of planetary seeds forming, which then get broken apart or there's not enough material around them to essentially create a whole planet. But they get heavy enough that they get really hot, and all this iron will sink to the center of that protoplanet. And when it gets broken apart, all that iron will stay together and cool off and create objects like these. It's thought to contain about 1% of the mass of the entire asteroid belt, which, considering how many objects exist in the asteroid belt, is a quite substantial amount of it. As I said, it's made entirely of iron and nickel. Its diameter is about 157 miles. So that is another mission to look forward to in the coming future. All right. With that, thank you for watching. Any questions you have, we'd be very happy to take them now.
And then after this, and then after the questions, we will open up Universe Sandbox and show some cool simulations.
And questions relating to the presentation are, of course, very welcome, but it doesn't have to be specifically about comets and asteroids. Any sort of astrophysics questions that you are thinking about, feel free to ask us as well. Looks like we have our first question from James. He says, oh, never mind. That's not one. This is a comment. All right. So
that is
any questions?
That is a good point, though. Yeah, they didn't even know really what had happened because it had landed in the shadow. And so they were like, oh, no, it lost power. But then it was like, how do we connect? But luckily, like 2 years later, as they were going, like as the Rosetta orbiter was still like going around the asteroid, they were able to make a brief bit of contact with it and actually confirm that it was right there. So not make contact, but like they managed to actually see it.
All right. Looks like we do have a couple questions coming in now. One is, are asteroids from the asteroid belt exclusively from there?
I think that is a no. They come from all over. Like the Oumuamua one was definitely from out of the solar system.
Yeah, I believe the asteroid belt is called so because there's a relatively large number of them, but you can find them kind of throughout the solar system and space. We have a question from Ashwath. Are new elements discovered in asteroids?
I think at this point we know most of the elements.
Yeah, certainly no heavy unstable element is going to be found in one. A question from Steve. Why was OK considered a meteor, not a comet?
I might have misspoken if I called it a meteor. It was an asteroid specifically. A meteor is when it actually ends up in the Earth's atmosphere and burning up. But in that case, it was either an asteroid or a comet since it did not impact us.
Right. And specifically, meteor is the bright light that's emitted by these objects when they go through the atmosphere. Mm-hmm. So both a comet and asteroid impact could create meteors. We have a question from John. Are there future plans for Voyager-type probes visiting the outer planets, such as Neptune and Uranus?
I'm trying to think. I don't think there are any ones that are like Voyager type or like aiming for the outer planets.
Yeah, there's nothing solidified. In a conference I went to last year, there is a group that has been trying to propose and get a mission funded for many years for an extra stellar probe. So essentially something like Voyager that would leave our solar system. The plan would be to, as opposed to visiting the outer planets, just get as quickly as it can out of the solar system. But as far as I know, they're still just proposing and trying to get money.
That is definitely the hardest part of all of these, is convincing like the funding places like the NSF to give you money to do your mission, to go out and do all this stuff. That's absolutely the hardest part of it.
And there was a really interesting aspect of this project, which was because there was an extra solar probe, something designed to leave the solar system and then begin its science mission. It would take decades to do this. And so it was a unique organizational challenge of how do you have a science team where the people who are on it at the very beginning will likely be retired or even passed away by the time the mission is ending, and have all these generations coming and going over its lifetime. And it was something you wouldn't think about because we don't usually have 30, 40-year missions, but that was an interesting thing to see them talk about.
With the question about why is Halley's Comet so rare, we can actually use that as a transition into the activity if you'd like, and then we can answer some more questions after. But I can show you a simulation, because it turns out Halley's Comet has like a really wide orbit. Like it's just really, really big. So it just takes forever for it to go out there and come back. I'll share screen. Did that
stop share?
Okay, I think my screen should be visible now with Universe Sandbox. So this is a program that you can go download. I think it's pretty cheap or whatever. I got it for free at like a conference, and you can simulate things. So like right here is just literally the solar system. You can control the time step, you can add random objects, like I could just add another Earth right here and see how that messes things up. But specifically, I can start by showing the orbit of Halley's Comet when it last came by in 86, I think? Yeah. So here, right here, you see 1P/Halley, and as it, whoops, I zoomed in too far. And that's how it's coming right in, going around the sun, coming back out. Looks fine and dandy, but when you zoom out all the way to show how big its orbit, it is like way out here, like Pluto orbit almost. So it takes just a really, really long time for it to come back. So I don't think it's going to reappear until 2061 is the next time it'll come all the way back. Another comet or asteroid or whatever that I was going to show was the 2019 OK, the one that barely missed us. So this, I'm going to pause it for a second and zoom out. So you have the solar system. You have asteroid 2019 OK. Now you zoom in back towards the Earth. Keep going, keep going. Then you get to the orbit of the moon. And now you watch as you play. And this is just the Earth moving along, moon moving. And this is how close 2019 OK came to Earth. And we just did not see it coming, just because of the direction and just where it was and where we were in time. So that was quite interesting. Another simulation I want to show with this is that of, oh, it is not typing. There it is. Oumuamua's orbit. You'll notice how the other ones came in as like a circle, but this one comes in, sorry, I'm really bad at zooming in casually. This one comes in more in like a hyperbola shape because it's not in a circular orbit. It's coming in from way out of the solar system, and it is leaving way out of the solar system. So like if I simulation just to go faster, you can see it just shooting out here and just completely leaving us, just because it came in so fast at such another angle. That's how we know it came from out of our solar system. Another one is, sorry, I have it written down on my computer. So one of my favorite simulations is Earth and 200 colliding moons. Just because it shows all the collisions. So this is what would happen if we gave Earth 2,000 moons, or 200 moons. It would not be good. There's a lot of just fun simulations that people have already made on here like that just show stuff like this, that I think is just kind of amusing to play with, because it even shows like how it impacts like the Earth is now just a molten ball completely being destroyed. And then just to emphasize from the talk earlier how there are a lot of potentially hazardous asteroids out there, we've cataloged a lot of them, and oh, this one's taking a while to load. Like, these are just all the potentially hazardous things that could come near us. There's a very, very small chance, but they're out there. And a lot of like the larger ones are logged, but it's still just interesting to see them all. And I think with that, we can go back to Trevor, if you want to keep reading any questions that have any further come up.
Yeah, of course. There's another question from James, which is how much progress has been made on plans for Earth defense if an impact is predicted far enough in advance?
Oh, this was one of the labs that we taught. I can't actually remember. I know that there's not enough being put into it, but there are a bunch of telescopes like that have like pan-stars and other ones that specifically look at the night sky like every night and see if anything is changed, anything is different. So like there are plans that have gone out there to like spot the asteroids, but as far as what to do if there actually is one that's gonna hit us, I recall NASA doing a simulation at one point that they put on the internet where they simulated an asteroid that was gonna come and hit like Denver or Detroit or something, and in the simulation they tried to blow up the asteroid, and then instead it hit New York in their simulation. So that didn't quite work. I do also know there is one mission that I forgot the name of that they're going to try and crash, I think, a probe into an asteroid and just see how much it affects its course, but I can't remember the name of the mission.
Looks like there's another question from Ben, which is, do we have a gravitational influence on OK to throw it significantly off its orbit as it was so close?
I'd say, yeah. An interesting feature is if you look at Wikipedia for orbital information, you'll find that the Neowise comet, for example, it has like inbound and then outbound for like when it lists its orbital period and it's like how close it comes and all that jazz. Because when it comes in, like it gets thrown off by Jupiter for certain, and probably at least a bit by Earth. And so its inbound orbit that would have happened has now been thrown off and it changes. So yes, actually, yeah, I think Earth would also have an effect on that.
It would be similar to when we use plans for gravitational assist on spacecrafts. It kind of used gravitational assist from Earth, so it kind of got sped up and a little perturbed. There I have a question from Kurt, which is, what do you say to people who believe an unidentified planet X is coming?
I mean, I think it's out there. Yeah.
Yeah, there's certainly a possibility of other planets that we, can't see because it's even a hard thing to detect things like Pluto from Earth. I don't think it poses much of a threat to Earth if there is one. I don't think it's going to be colliding with us just because the chances of something like that happening are extremely small. But
like I've seen a number of talks on the topic of like they're trying to search for it by looking for trans-Neptunian objects, which are just objects out by Neptune's orbit. So like there are people, lots of people actively searching for Planet X. I just don't know how close they are to finding it.
Right. Planets don't emit their own light, so you have to find a very, very dim thing very far from Earth. It's extremely small.
Yeah.
All right. We have a comment from Ali. What are your thoughts on asteroid mining, and what is the earliest that would become possible?
Sounds dangerous.
So, anyone unfamiliar with asteroid mining, it's because, like we mentioned with the Hayabusa 2 mission, certain asteroids are, entirely made out of things like iron and nickel, and there are huge volumes of it. And so if we start to get to a point where Earth resources become scarce, you can start mining these asteroids to get really rare metals and minerals. I mean, high volumes, but it's not easy to get to them. Our current missions of trying to get better with lunar capable missions and Mars capable missions would certainly be big steps to that. Because if we want to try and mine asteroids, we better be able to get to where they are, which it tends to be in the asteroid belt, which is just beyond the orbit of Mars. So we're progressing towards having those capabilities, but we don't really have them yet, much to the chagrin of Michael Bay and Armageddon.
Well, is it easier to train astronauts to drill or to train drillers to be astronauts?
We know not to ask that question.
Yeah.
This is a complete aside, but a fun bit of information regarding using asteroid metals is because asteroids that were metal rich would land on the surface well before we had any sort of mining techniques on Earth. Ancient civilizations would find them and use them in tools. So the earliest sort of iron weapons that we have came from asteroid metal because you didn't have to do anything for it. It was just a solid chunk of iron sitting there waiting for you. And we know that a dagger owned by Tutankhamun, the child pharaoh, also came from an asteroid.
I read an interesting news article not too long ago that was just kind of about how people go out searching nowadays for like after an impact, like if they're searching for bits of like a meteor or meteoroids that have like gone to the surface, that like the article painted a picture of a team of like 20 scientists running through a desert or something on this one occasion, all with metal detectors, just searching because they have like a wide swath of area where they think the chunks fell to Earth, but they have no idea specifically where for some of them. And I don't know why, but the mental image of just 20 astronomers with metal detectors running through a desert is just rather amusing.
And if you want to try and find fallen meteoroids and asteroids, your best bets are places like deserts and Antarctica, places that are large, flat. You can definitely tell if something came from space and isn't supposed to be there. I believe there was even a Discovery Channel show on like meteorite hunters where they would like try to find them and then sell them because they're very valuable if you can find a large one. All right. I don't see any further questions.
Okay. Right now, I just pulled up a simulation that shows where Voyager 1 and Voyager 2 are right now with regards to everything in the solar system. So that's kind of cool, in case you were wondering. Or not right now, but as of last year, because the simulation starts in 2019. But yeah.
My favorite fun fact about the two is that Voyager 2 was launched first, and then Voyager 1 was launched after.
Astronomers and their naming conventions.
I think it was because Voyager 1 got the sweet spot launch of getting all of the assists to do the grand tour of the planets, and Voyager 2 kind of got the, it's still an okay launch window, but not as good window.
Sounds about right. I'm gonna stop sharing there. Okay, yeah, that seems to be it for questions. So if no one else has any others, or if there's any other thoughts that you have. Oh yeah, I did remember there was one other thing I wanted to screen share. Hold on, where did that window go? I have too many windows open. This tab. So there's some other websites that you can go to that are less intensive. But so this one is called spaceinthreed.com. And you can just look like in the web, like just kind of current information and like to a lesser degree, all this type of stuff. So like right here is the Neowise comet, like where it is right now, where's the sun, Earth, and just all of that information. So this website just has like a wealth of information. So like actually, we can even look at where Ryugu and Bennu are right now. which not everything is built into Universe Sandbox. Like you can put stuff in, but the interface isn't that easy. But this website right here is just like super useful. So like here's Bennu right now. Like it is a near Earth asteroid. Like it is pretty close. And it is going at 24.8 kilometers per second. That's fast. Not super fast, but fast. Yeah. So I think, yeah, so this is the website, spaceinthreed.com, if you're interested in that.
All right, and as Nico has stated in the chat, Nico is a fellow graduate student of ours. Next week, we'll be having the last Universe at Home event of the summer, and it will be on current events in astronomy. So what are the major discoveries and events people have been talking about and making and publishing this summer?
And I think without any further questions, that just about wraps it up. Any last thoughts, Trevor?
No, just thank you everyone for coming, and if you've come to previous events, your participation has been greatly appreciated by us.
All right, thank you all for coming. Farewell. Okay.